Hello, today we talk about two-state quantum systems. In classical physics and classical information theory, you can have in a two-state system two possible states like 0 and 1, which can represent, for example, on and off in a circuit, and in general they represent real physical quantities which can be measured, which can be observed. Instead, in quantum mechanics, a two-state system means that it has a maximum of two independent states. Why? Because the systems in quantum mechanics are not simple sets, but they are whole vector spaces, and they are complex vector spaces. So a state can be represented by a linear combination of two basis vectors, which can be 0 and 1. So this is now a basis. Is not the whole system, but a basis for the system. And these are complex coefficients, and they represent the probability of measuring the state and obtaining a particular result. For example, alpha, the modulus squared of alpha is the probability of obtaining the result 0 when you measure psi. Instead, you have probability modulus of beta squared when you are measuring 1 when you measure psi. And so since they are probability, they must add up to 1. If they don't add up to 1, you can also consider those states as the probability are normalized, must be normalized by dividing them by alpha squared plus beta squared, so that the sum of these is 1. So if you multiply this by any constant, you don't change the state, because you simply then you have lambda, then the probability will be lambda squared modulus of lambda squared modulus of lambda squared, and you simply will have to normalize again, so it is automatically normalized because you must also substitute lambda squared here, and you have the same physics. So you can multiply psi by any complex number and it will be equivalent to psi. It will represent the same physical state. Now, we had expanded psi in this basis 0 and 1, but we can choose a lot of bases. For example, if we are studying spin, a basis can be spin up, spin down. Another basis can be spin right, spin left. Since they are bases, it is important that the two vectors inside are independent, and you can write psi as a combination of these bases or a combination of these bases. And if you measure psi, you will get one of these two values if you orient the measurement apparatus in the up-down direction, in the vertical direction, and one of these two if you orient the measurement apparatus in the horizontal direction. So it is useful to expand the vector in the basis according to how you, depending on how you orient the apparatus. In fact, measurements in quantum mechanics are represented by matrices, in particular matrices, and they act on the vector and they will change the state of the vector. For example, once you have measured psi and the measurement will return one of these two values, then psi changes state in one of these two eigenstates. If the result is up, we get this state. If the result is down, instead you will get this state. And then these states will evolve with the Schrödinger equation. But in the instant after you measure the state, they will be with 100% probability in this state, and it will take some time for the probability to spread out again. So we will do some algebra with the states, and we will do it with matrices, and these matrices must be Hamilton because their eigenvalues will represent real physical quantities, and so they must be represented by real numbers. And Hamilton matrices have this property, they have real eigenvalues, so we want to restrict to Hamilton matrices, and the algebra will be in a four-dimensional space, the algebra for two-state quantum systems. In fact, a generic 2 by 2 Hamilton matrix will have the form A, B, C plus ID. Conventionally I write C minus ID and C plus ID. So this is the most generic form for a 2 by 2 Hamilton matrix. So we have a four-dimensional space for operators, and they can have bases, for example this, and you see that this matrix is the combination A plus B this plus C this plus D of these four basis matrices. But this is one possible choice of basis. This is not the most common one, because we usually want to isolate the identity matrix, because identity matrix applied to a state will not change the state, and the span of identity matrices, which is the identity matrix multiplied by an arbitrary constant, will represent things like shifting the energy by a constant value, so things which will not change the mechanics of the system. So we want to get rid of the identity matrix and only studying the algebra of the other three basis matrices. So we write the identity matrix, and instead of these two matrices we have the identity matrix, then we have 1 minus 1, and then we have the usual as before. Now this matrix is the identity, and this matrix is sigma 1, this is sigma 2, and this is sigma 3. They are the Pauli matrices. So we want to study these Pauli matrices, and it is easy to verify that they have eigenvalues 1 and minus 1, but we can do better and prove that any combination of these three matrices will have eigenvalues 1 and minus 1 if the combination vector A has norm equal to 1. So what is this vector? This vector A, we can write a combination of these as A scalar product sigma, where sigma is a vector of matrices, so sigma equals sigma 1, sigma 2, sigma 3, and A is the vector of the coefficients A1, A2, A3. We write it x, y, z, and so this would be x sigma 1 plus y sigma 2 plus z sigma 3, and this is x minus yi, let's write iy, plus iy, z minus z. And we have x squared plus y squared plus z squared, the modulus, sum of the modulus equals 1 by hypothesis. Now, this matrix we always have eigenvalues plus 1 and minus 1. In fact, we can calculate them directly. The determinant of this minus lambda I is that minus lambda times minus z minus lambda, which is minus z plus lambda, minus, now these x minus iy times x plus iy is equal to x squared plus y squared, and all this is equal to minus z squared plus lambda squared minus x squared minus y squared, and this is the modulus squared minus modulus of a squared plus lambda squared. So we have lambda squared equals the modulus of a squared. So since lambda is real because this matrix is Hamilton, we have lambda equals plus or minus 1 because the norm of A is 1. Now let's find the eigenspace for each one of the three matrices. So we start from sigma 3, which is diagonal, so it is very simple. In fact, we have for eigenvalue 1 minus 1 minus 1 minus 1, so we have 1 minus 2, which gives the eigenvector 0 minus 2, which gives the eigenvector 0 1, and then for minus 1 we have 1 plus 1 minus 1 plus 1, so we have 2 0, which gives instead 0 1. So here we have this eigenspace 1 0 with eigenvalue 1 and 0 1 with eigenvalue minus 1. Then we calculate the eigenspace of sigma 1. We have eigenvalue minus 1 minus 1, which gives which gives 1 1, x equals y, and minus 1 gives 1 1 1 1, so x equals minus y, so 1 minus 1. So this is the eigenspace of sigma 1. 1 with eigenvalue 1 and minus 1 is eigenvalue minus 1, and then we have sigma 2. We have eigenvalue 1 minus 1 minus I minus 1. So we have y equals, now I'm writing xy vectors as xy, we have y equals ix, so we have the eigenvector 1i, and instead and if we normalize it, we have this divided by the square root of 2. Same thing for these two vectors we have found before of sigma 1, and then we have this eigenvalue minus 1 minus I 1. I'm checking if you can see. So here we have 1 minus I, and normalize is divided by the square root of 2. So we put them here, 1i divided by square root of 2 and 1 minus I divided by square root of 2 with the value minus 1. These eigenvectors are commonly written as, this is written as 0, this as 1, this as plus, this one as minus, this one plus I, and this one minus I. Now, when studying spin, these matrices, a combination of these matrices, represents the measurement of the spin in a particular direction. In particular, sigma 3 is a measurement of the spin in the z direction, which can give results up or down. So 1, 0 represents spin up and 0, 1 represents spin down. Sigma 2 gives which we can call sigma x, gives the measurement in the x direction, sigma 1, sigma 2 in the y direction. The eigenvalues of these matrices represent the possible outcomes of the measurement of the spin. So if we want to represent in 3D space these eigenvectors, this one represents the up direction, so we put here 1, 0, and this one is the down direction, so we put here 0, 1. This is the right direction. So in the, let's say, in the x-axis, 1 over square root of 2, 1, 1, and this one is 1 over square root of 2, 1 minus 1, and here we have the y-axis, and we have 1 over square root of 2, 1i, and 1 over square root of 2, or 1 minus I. So in this representation, opposite directions represent perpendicular states. So we have it 180 degrees perpendicular states. So if we were drawing instead the state space, we will have here 1, 0, and here we will have 0, 1, while instead here it is rotated on a full 180 degrees. So when you go from the state space to the actual physical space, the angle doubles, and you can create a sphere with these directions, which is called the Bloch sphere. And any point on the surface of the sphere, of this sphere, represents a state psi with norm equal to 1. If the magnitude is different from 1, then you are outside the sphere, and inside the sphere if it is less than 1, and outside the sphere if it is more than 1. And if we restrict to the states on the sphere with magnitude 1, we can write them as, for example, as combinations of 0 vectors 0 and 1, and since alpha squared plus beta squared equals 1, and since we can shift this by any phase without changing the meaning of the state, so without changing the physical state, we can choose to have here phase 0, so we can write here cosine of theta half, and here the coefficient becomes e to the I phi, so a phase shift times sine to theta half. Now why have I written theta half instead of theta? Because this theta half is the angle between these two states, 0 and 1. This one is 0, this one is 1. So in the state space, we have here psi, and this angle is theta half, because remember, when you go from the state space to the physical space, the angle doubles, so they are separated here by theta. So I have chosen theta half because with theta I represent the physical angle. So we have that theta theta half is between 0 and pi half, right? And so theta is between 0 and pi, and phi is between 0 and 2 pi, so we have recovered the whole 3D sphere. You can check that the way we put the eigenvectors on the axis is compatible with this notation if theta represents the usual angle from the z-axis and phi is this angle. So if theta and phi are the common the common spherical coordinates, you simply write the state in this compact form here, and you substitute theta and phi. So here we have theta equals 0, phi can be anything. Here we have theta equals pi, and here we have in the x-axis theta equals pi half, and so on. So phi equals 0, and here pi half, and phi equals pi. The same thing for the y-axis, you have pi half and pi half and pi half and 3 pi half. So on the x-axis you have 4 plus x, theta equals pi half, phi equals 0, and here instead for minus x you have phi equals pi and theta also equals pi half, and so you substitute here, and pi half is theta half here is pi by 4, and so we have the cosine of pi by 4. Here we have the sine of pi by 4 times e to the I0, which is 1. Here we have the same thing, but we have a phase of pi, and e to the I pi is minus 1, did the Euler formula, the Euler identity, and so we have minus sine of pi over 4, and cosine and sine of pi by 4 is 1, and so here we have 1 minus 1, which is exactly what we got before. And so we guessed right for the x-axis. Now we check for the y-axis. We have here plus y, and here plus y, here minus y. Remember, we should get 1i, and here 1 minus I. So we have here now here we have phi equals 0, and here instead we have phi equals 3 pi divided by 2. Here we have phi equals pi divided by 2. Here we have theta always for pi divided by 2 like before. So we have 1 times the phase e to the 3 pi divided by 2, and here 1 times the phase e to the pi divided by 2. Now e to the pi divided by 2, this phase is I. So here we have 1i. So this phase gives I, and this phase instead gives minus I. If you remember the complex plane, you can evaluate these exponentials very quickly. And it is exactly what we had guessed before. Now we check with the z-axis. We have here cosine of pi over 2, and remember that here of theta over 2, here theta equals 0, and here theta equals pi, so theta half equals pi half. So here we get 1, 0, and here we get 0, 1. Notice, by the way, that here we have a singularity, because here we should put e to the i5. Here e to the i5 gets multiplied by 0. Here instead we remain with e to the i5, so we are at the poles, and phi can have any number. There is the singularity at the poles in the sphere. So by convention we choose phi equals 0 at the poles, so that here we get the vector 0, 1. So we managed to represent the spin geometry on a 2D surface of a 3D sphere, and we could do this because of the complex nature of these vectors. These vectors on the Bloch sphere are called spinors because they represent the spin geometry. Rotations on the Bloch sphere are particular operations which can be represented by matrices, and these matrices for the group SU2, which is the group of the unitary matrices of determinant 1. Unitary means that U dagger times U equals the identity. U dagger represent the transpose conjugate. So this SU2 are the rotations on the Bloch sphere, exactly like SO3 are the rotations on the 3D sphere, and they are very similar. They all can be represented on a sphere. They all represent rotation on a 3D sphere, but they still have clear differences. For example, since the state minus psi is equivalent to the state psi, here two vectors, one opposite to the other, they lie on the same point. They represent the same point of the sphere, right? So 1, 0 is the same as -1, 0, and it is in general the same as e to the i5, 0, where i5 represents a shift in a particular phase, and here instead v is clearly in a different position than -v. -v is in the opposite direction, so they clearly represent two different points on the sphere. So here we have two entries, complex vectors, and here we have three entries, real vectors, and there are a lot of beautiful correlations which I may leave for another video. So this is all for today. See you next time. It has been a pleasure.